right. Hello, everyone. Welcome to the International Methods Colloquium. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Pete Mohanty from Stanford University. His talk is entitled Messy Data, Robust Inference, Navigating Obstacles to Inference with BigKRLS. And before I introduce Pete, I want to apologize both for not being in my office and also sounding bad, maybe collapsing into coughing. I got diagnosed with pneumonia yesterday, so I'm doing this from home and a lot less animated than I usually am. So Pete's talk, despite my illness, will last between 30 and 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. A link to Pete's paper and his slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I'll post those links right after we get started. Now I'd like to welcome Pete to the IMC. Pete, welcome.
Hi, thanks very much for having me, and thanks for sticking it out in spite of adverse circumstances. And actually, last week there was sort of the convention, if someone had a clarification question, you can go ahead and ask that, and I'll just, otherwise I'll take the bigger questions at the end.
Sounds good.
Presenting a joint work with Robert Schaefer, who I believe should be out there in the audience, and we've been working on big kernel regularized least squares, which is why are we not advancing here? Hold on one moment. Okay, there we go. This is a technique that we like because it allows you to make inferences about your data despite the fact you might not know a whole lot about where they're coming from. And as we'll see, this can help you in both the observational and the experimental settings. The kind of trade-off that we're going to be discussing is, as well as the examples, stem from the fact that this is a very computationally intensive technique. The two big worked examples that we're going to talk about are treatment effect heterogeneity in a GeoTV field experiment. I imagine a lot of you know this paper if you're kind of tuning into this talk. It deals with the role of social pressure in elections. And we're also going to be talking about the observational setting and looking at how something like KRLS can help you where you might otherwise have to fit a model that's hierarchical or involves a lot more assumptions. And so this will help us in that setting as well. The challenge is that because we're allowing the model to consider lots of possible curves, it's just simply hard on the computer. And so we're going to do a mix of things to try and alleviate those concerns. One is we've switched to the C++ environment, so the user will interact with our package in R as usual. However, we're going to get serious speed gains, and we're also going to be able to handle large matrices much better using the big memory package. To help just make sense of all of the rich results that you get out of this technique, we've also set up a Shiny feature so that you can with one command start interacting in your web browser with your results. In addition to some software improvements, we've done a lot of work on the algorithm to make it scale better, both in terms of sample size and the number of explanatory variables that you have. We'll see that as a particular challenge because we're not just looking at average marginal effects or something like this, but we're really looking at much more nuanced changes, and so it was important to work with a large number of X variables. And the binary variables for this algorithm, the first differences estimator for them is really quite useful, but it was even more computationally intensive than everything else because it involves sort of a counterfactual comparison. And so we've derived a new estimator on that front that has a leaner memory footprint. And finally, I'm going to talk a little bit about what this means in a slightly bigger context and how data science can help us in social science and what kind of trade-offs we're going to encounter. So as I started to say, we're going to talk about how, or one of the reasons we like this technique is it allows us to make quite a few inferences while minimizing our assumptions. It's very accurate out of sample. Robert was recently working on a project where he's actually slightly beating random forests with this technique. I don't know that that would always hold up, but it really does quite well out of sample. And there are closed form estimates for those predictions as well. One thing that's very nice is that we're not just getting the so-called average marginal effects, but we are going to be estimating the marginal effect at every single point in the X, the set of observations. So very rich results. And in comparison with other results, other techniques that are out there that have some of these nice properties, we think that this one is more interpretable because it is more similar to the type of regression training that most people have, which allows us to kind of think about the effect of one variable holding the other one's constant and that type of thing. And so there's a nice interpretability feature to this, and that's part of the reason it was designed as such. The paper that we're going to be building most directly on here is Heinmüller and Hazlitt's work in political analysis, which works out a number of nice properties of this technique, some of which we'll be talking about here. For a more general introduction to this approach, I recommend Trevor Hastie and some of his co-authors have a couple of textbooks on statistical learning, which will get you started on this and related techniques. Hazlitt has done some, Chad Hazlitt has done some nice follow-up work as well, even taking further steps to help observational studies approximate experiments and get unbiased estimators of the average treatment effect, the ATT. So if that's something that's of interest, certainly check out his work. And, as we'll see in just a moment, a lot of people in this area will look at the regularization or the regression penalization structure as almost like a type of Bayesian prior, because we're saying that we're skeptical of certain estimates, but we're more persuaded by others. However, if you're interested in a full-blown Bayesian version, Zhang has a very nice implementation with Michael Jordan up at UC Berkeley, where they give links and even some multi-level options. And so I wanted to point out that work as well. Okay, so here's the basic idea. We don't know where y is coming from. It's some function, but we assume it's going to be that we can approximate it as a kernel multiplied by a set of weights c. And our kernel is going to be a Gaussian kernel. And more particularly, we're going to square the Euclidean distance between each observation I and j. And we're going to divide by a bandwidth parameter, which we're going to set to the number of observations. The number of explanatory variables, which is, we're going to call that p. But the idea is that we're going to get some score of how similar each pair is between 0 and 1. And we're going to store all comparisons in an n by n kernel. And then we're going to look for a C that's going to help us explain what's going on there. However, if we were to do this, just kind of go through blindly, we would always be able to find some vector C that helped us get back y. And we don't want to do that. We don't want to go after outliers for our explanation. So we're going to do a regularized framework. The penalty or the regularization is over here. Let's set that aside for a moment. Our ultimate goal is to look for some vector c such that kc gets as close to y as possible. So that's what we're looking for. However, we are going to have this squared penalty, and it's actually going to be a weighted square. A little bit the way that this works is that y is going to be standardized, as is x is going to be standardized before we do this. So values that are close to 0 are going to be ones that fit well, whereas if you square these coefficients, which are also going to have mean 0, that's going to be talking about an outlier. We're going to weight those outlier terms by the similarity matrix as well. So that's why the regularization is kernel regularization. And so those are the different places it enters the formula. So we're going to have this other vector that we're interested in of weights. We're going to call this C star, which reflects both our overall optimization goals as well as this penalty. For those of you who were here last week, someone was talking about the Bayesian version of the lasso. I just wanted to point out two quick differences. Here, we're talking about Euclidean distance, unlike the most typical lasso, which works with an L1 penalty or absolute distances. And the other is that the minimization is something like x beta. It is, you have however many parameters you have, typically similar, maybe a little bit larger than the number of x variables. Here, if we have n observations on the dependent variable, and this is n by n, well, to make this conformable, we also need to get regularization for every single observation. We need to regularize n terms. And so that's part of where the computational complexity comes from as well. Under assumptions that are largely analogous to classical regression, such as this having mean 0, which of course it does in practice, you can show that KRLS is unbiased and consistent. We'll get an unbiased set of estimates of the coefficients, and we have closed form estimates of their variance, and it can be shown that those are consistent. And so it's a very nice setup, and everything is pretty much closed form front to back. A little bit of exception. We have to do a little bit of numeric work to find lambda, but there's a lot of math saying that we can do this in a reliable way. Okay, so here's the notation that I'm going to use for the marginal effects. If we have, say, 10 explanatory variables, we're going to estimate n times p of them. Each of these is going to be a vector, and I've chosen delta to represent the derivatives. And just, we could pick without loss of generality the second one. Let's say that it's the income of the respondent. The way that we're going to estimate the derivatives is by looking at the simple distance in terms of income between each pair of observations. And then we're going to weight the kernel by that. And this is simple multiplication here. And then we're going to do some matrix multiplication with our estimate of the coefficients. And the idea is that, are we explaining some difference on this dimension that we wouldn't have explained otherwise? It's a little bit how I look at that, those terms. And we also wind up dividing by sigma squared, which is again just going to be set to whatever p is to help us make sense of the results. That's another little thing that's going to make us skeptical of including too many variables. If I include 1,000 x variables, then every derivative I tend to estimate is going to be that much smaller. And so that's another little check on being too data-driven about things, so to speak. And the average marginal effects are the column means of this matrix. That's our estimate. And to the extent that the data generating process is actually linear and additive, those estimates will converge with what you might get with OLS or some other parametric approach, whereas they could be quite different if in fact those assumptions are met. So we're just going to do a quick illustration. This is what the R code looks like. I'm going to take 5,000 draws for two x variables, and we're going to just say that our outcome y, our target function is going to say that we have sine of x1 and plus x2. And what's nice about this is we're not going to tell KRLS to look for any kind of curve. We're not even going to tell it that there may be a curve. We're just going to give it the data matrix and see how it does. So take a quick moment to look, but it actually does pretty well. We know that if y is a function of sine of x, then the derivative is going to be cosine of x, and I've put the cosine of x in blue here. It gets pretty close to that, but you do see a couple little things going on besides the fact that it gets relatively close. One is that a different interpretation of the regularization process is to kind of prefer smooth curves to jagged curves. And you can see that looking at each of these 5,000 estimates of the marginal effects, that it kind of wants to cut the corner a little bit. It's not quite sure that it needs to go all the way down here. And it does a little bit better maybe towards the middle than towards the endpoint, but for the most part, it's being a little bit cautious about going all the way down to the curve. And so I've actually done a slightly more formal way of thinking about this. We're getting 86% of our estimates are smaller. Actually, I shouldn't say slightly. 86% of our estimates are smaller in magnitude than the true target function. So we're covering a complicated curve without having to know to look for it, and we're also not overestimating the curviness. I should say that part of the motivation for optimization is that this curve looks better and better as sample size grows. If you have less than 1,000, it's really not going to think that you have real evidence, and so you're going to have a pretty flat scatter. Okay, so why optimize? One is simply speed. Luke Sonnet is a grad student who works with Chad Haslett down at UCLA, notes substantial speed problems with the R algorithm starting around 1,000, but has made some headway in the scientific computation language of Julia. The other is size. Here's a quote from the authors of the non-parametric package NP. The Tikhonov regularization, the kind we're doing here, requires computation of weight matrices, which are n by n, and may be unsuitable for large data sets. And in fact, not only do we have to work with n by n matrices to get our regularization parameter, we're going to have to continue to work with them to keep getting these estimates of the derivatives. So in practice, most typical machines, and by which I mean I've tried the R algorithm on a number of laptops and even a couple of servers, they start hitting cannot allocate vector. They're basically running out of memory somewhere around n equals 3,000. Okay, so here a little bit more detail on the updates of our package. We re-implement, at this point, almost everything that's a substantial calculation is done in C++. A number of people prefer using RCPP. And Armadillo is just a particular C++ library, which is going to allow us to do most, maybe not quite all, of what we would like to do. We did wind up having to implement some helper functions, some linear algebra things that we just didn't quite have in the right form. But for the most part, we're able to do an awful lot with this library. We have reduced just the memory footprint considerably. The original algorithm, the memory footprint was proportional not only to the number of observations squared, but also to the number of derivatives that needed to be calculated, the number of x variables, and that got bad pretty quickly. Just to give an idea, if you haven't kind of played with this type of problem before, when we say the number of observations squared, you have to multiply that by the size of each individual number in bytes, and you wind up with something like once you cross n equal about 12,000, each 12,000 by 12,000 matrix will be about a gigabyte. And so in terms of the overall footprint of these calculations, you're talking about, you could have, some X matrix that's really quite tiny. It would actually fit on a floppy disk. 20,000 observations, 100 X variables, whatever it is. That's going to be pretty small. But when you start squaring this, the overhead calculations, might not even fit on a DVD. So this is, it's really dramatic, and part of our motivation is not to solve this problem once and for all or something like this, but rather to extend the possibility of what a typical machine can do for a class of sample sizes that are relevant to social science and related researchers. Big memory helps us do this a lot. We are able to bypass some of the harder memory limits that R imposes. You're able to handle everything as a pointer. If you've worked in C++ before, that kind of gives you savings there. And we have this ability to write to swap if need be. So these are a little bit like bumpers in pool. If you run out of RAM, you at least have the option to temporarily put something to the hard disk. That will give you speed compromises, but it still allows you to kind of push what any given machine can do. And I've already mentioned a bit about the Shiny. I'll see a little bit of that in a moment. Parallel processing was something we looked into at the beginning of this, and it solves some but not all of the problems with this. You know, of course, you have this fundamental n by n problem, and the big memory package is great for certain things. It's not great for distributed computing. It's okay for parallel computing. We actually did an earlier version with parallel processing before we had switched to this environment. And we are looking to in the near term to switch back, particularly for the derivatives, because then you're just really doing very similar computations for each of your x variables, and so that'll give us speed gains, even if it doesn't really give us sample size gains. And so here's our first example. This is this classic paper by Gerber, Green, and Larimer, where they wanted to know whether social pressure was the mechanism that explained whether people vote or not. And so this was done back in 2006, and they randomized what type of mail people received, either ones that contained some sort of pressure or not. And they targeted people who had at least a variable chance of turning out to vote. So they, from public records, inferred whether you were always voting or never voting, and then they gave people a gentle nudge to see. Part of our motivation for looking back at this is that Green also did a great follow-up paper in political analysis where this was used as an experimental benchmark for polynomial regression. The feeling was that the treatment effect was heterogeneous by age, and we concur with that. And so they allowed for the possibility that the treatment effect interact not only with age, but age squared, age cubed, and age to the fourth. And this polynomial structure allowed them to kind of fit a curve, and so that's nice. But our question is, what if we didn't know to look for that particular structure, or what if some of us were persuaded by that particular functional form, but others were not? Is there a way that we can be a bit more agnostic and still get a good handle on the treatment effect heterogeneity? Here's an example of the treatment. It's kind of funny, although I don't think anyone's really just laughing about the election just now, but it's this funny bit here of whether or not your neighbors knew you voted. Of course, it is public record, and so they sent a mailer where that was revealed, and there was also some indication that they were going to follow up with this and let the neighbors know whether you voted this time or not. And this actually increases the chance that people who are on the fence will vote. So here is the treatment effect. We've got the marginal effect all the way from age 20 to 100. The OLS estimate was a bit higher, more like 10% more likely to vote. So first off, we're a bit more cautious than that. But we also see that the treatment effect really peaks in the 40s, maybe 40 to 50, 60, something like this. Somewhere around 8% for this group, whereas young people, maybe they don't read the mail, maybe they don't care, I don't know, but they seem to hardly respond, and then older respondents, it trails off as well. So this would help you, if this is your study, maybe do a follow-up study to really confirm the functional form, or if you're more of a practitioner, maybe you would target your mailer to one group or another. What I've done here, since the coefficients also tell us how well you fit in the model, is I've colored each point by their fit, and this would give you a visual way of diagnosing if you saw that all the estimates that fit really well are clustered at a certain age group, whereas you have the darker purple colors down here. That might give you another reason to be skeptical of making a big general claim. So we're really gaining quite a bit of information, and I'm just going to flag this because we're going to look at an observational study next. This is not smoothed in any way. This is the exact set of. I believe this is actually a sample of 15,000. Doing this on 30,000 was a bit tricky on the computer I was using when I put this together, but we did a few of them. But this is 15,000 marginal effects, and they fall very neatly on this line. You do not get that in the observational setting, and so this also underscores why you would prefer experiments if you have the choice in the matter. Okay, so here is our example from January, whether people prefer Trump over Hillary. This is back in, of course, the primary season. We're using some Pew research data. And our dependent variable is going to be not terribly messy, but somewhat messy. It's going to be the difference of two Likert responses, each of which appears to violate the assumptions that you would normally use if you were doing like an ordered probit or something like this. And so certainly their difference is going to have an unclear distribution. And so what we're going to do is see how we can do without making that type of assumption on the dependent variable. And we're going to include very standard socio-demographic and sort of ideational variables, as well as state and region. Despite the fact that we only have 2,000 observations, because of the computational intensity of the first differences, this actually would have been tricky to do under the old setup. Okay, so here are what the results look like. I'm not going to spend a long time talking about this, but just to point out that we are getting p-values that go along with each of our estimates of the average marginal effect, and so that's nice. And the binary variable indicates whether we're doing first differences as opposed to something continuous. The model fits the data quite well, and you see a lot of patterns that we heard about for the remainder of the year, even in January. Certainly, self-identified liberals, minorities, people outside of the South or certain Midwest places preferred Hillary to Trump, and so the model kind of passes the smell test. And the R-squared is 0.68. However, the R-squared is an estimate of how much is explained by K and C star, or C star hat, I guess you would say, but how much do the coefficients explain along with the kernel? What we started doing is reporting what we're calling R-squared of the average marginal effects, R-squared AME, as well, because it certainly could be the case that this set of average marginal effects isn't doing the explanatory power, but more complicated curves, something that doesn't meet the eye, is in fact doing that. So in this case, we have about 80% of our explanatory power is coming from the average marginal effects, and that's an indication that it's fairly linear and additive, certainly not all the way. And that number can differ pretty dramatically depending on what type of data you give it and the approximate functional form. So we think that that's an important number to have a look at. Here is this variable estimates of the marginal effect of gender by state. In fact, you might not quite be able to see, but what we have here is the red end of the spectrum is 0, indicating sort of neutrality amongst women towards Trump versus Hillary. It was never big in favor. And then the blue colors are a big swing towards Hillary. And so this is nice to look at because we saw this average marginal effect a couple slides back saying that women prefer Trump, holding everything constant quite clearly. But now if we look at it state by state, we see quite a bit of difference, of heterogeneity, the kind of thing that one would normally, if you had a varying or a random effect, that would be good at capturing this. But this is nice because we don't necessarily have to make the assumption of specifying that in advance or adding that kind of computational intensity. It helps you be a little bit robust towards omitted variables. One thing we didn't put in this particular regression deliberately was any information about what people thought about Bernie Sanders. And you see that women are pretty indifferent between Hillary and Trump up here in the Northeast, where Bernie had something of a stronghold. And then we can, of course, look at other states and see whether it makes sense. So, we don't have a nice blue color in Florida, for example. So yeah, so you can really learn quite a bit from this type of thing. This is another one that we have on the x-axis age and marginal effect of liberalism. This is very, very close. This is basically what is released with the package right now, where you're able to get this with basically one command after estimation. And you see that all these numbers are negative, which in this context means that all liberals, all people who call themselves liberal, prefer Hillary to Trump. However, that effect was more pronounced amongst older respondents than it was amongst younger respondents. Now here, you see I have smoothed this to show the trend. If you look at this, because we're in the observational setting, it looks more like a scatter plot. The points are kind of all over the place, and you have the option of looking at that as well. So this is not to say that we're getting something that's as clean as we were with the voter experiment, but it might motivate a future study in that direction. Okay, so now kind of switching back to the optimization front, just going to point out the major steps of the algorithm and what the challenges are, and then a bit of what we've done. We are using here, this is pretty standard in computer science, but might not be the notation you're used to. The big O indicates the order of complexity. So we're sort of omitting smaller details, but we're interested more in things that are going to be the limiting factor, which for the most part is the thing that has the highest order of magnitude, although we'll get to an exception of that in just a moment. So of course we standardize everything first, and next we calculate the kernel. Now actually this is not a limiting factor in terms of speed, unless if p were to go really large in terms of n, this would kind of approach n cubed, but for the most part we're getting this without too much fuss compared to the other steps. However, once we set up these n by n matrices, each one of them is going to have this n squared memory footprint, and that's going to be bad. And a lot of the name of the game when we were doing this is really just counting out and looking to minimize every single place that we could either get rid of an n squared matrix that we were done with, or look for ways of circumventing computing it in the first place. To get our regularization parameter, we first need to do an eigendecomposition of the kernel, and that is costly in terms of speed. Then we use that to get the parameter by a numeric search. Certain properties guarantee that the parameter exists. And it's a single peaked function, and we just have to go kind of do a golden search to get as close to the peak as possible. So these have the same order runtime, but actually this is slower, and it can get slower still depending on how close to the true peak you want to get. And then we kind of keep using these things to estimate our weights. And then we almost don't mention the runtime component of anything where we have an n by n multiplied by a vector. It's hardly worth mentioning. What does get slow, and what is worth mentioning, the constant p, the runtime on the derivatives. We have to do for each of these, we have to do a lot of matrix multiplication. In some cases, triple products that are just really taxing on the machine. And so if each of these was to, if I was to take an hour for one derivative and you had 24 of those, then it would take a full day. And I have run this algorithm for a few days at a time. It's stable, but it'll get slower here. And so we're hoping to divide P by the number of cores that are made available, or at least roughly that's what parallelization will help once it's re-implemented. And we'll point out that the original setup, the memory footprint here was Pn squared. We were at least able to make it independent of the number of derivatives that are being estimated, and that was probably the single largest improvement in terms of sample size and then followed by the one that we're going to discuss next with binary variables. I've also omitted these later steps are followed by uncertainty estimates, which are also n-cubed for the most part. Okay. So here are some speed tests of our algorithm versus the original R algorithm. We are big R, and we're the lower color here, even though we're the upper color here. For some reason, it looks like we're getting the eigenvectors much faster, particularly as the sample size grows. We're getting the kernel much faster using the C++ big memory and some related packages. We don't seem to be doing much better in terms of cross product. Cross product is one of those things that, since you know that the form of the multiplication, R actually implements it very, very well. And so we actually implemented a version, but actually R does it so well already. R loves matrices, right? That we aren't getting speed gains here, but we're at least holding our own. We're not really losing anything here, whereas we're getting a bunch of gains elsewhere. And that's been a little bit the story here. You know, I've been saying how RCPP, Armadillo, and Big Memory and so on is better, but it's not like you're getting uniform improvements at every single step. It's more like you'll get a bunch of improvements, and then you have kind of setbacks elsewhere. You need to write new code to kind of fill in the gaps and that kind of thing. But in general, we're seeing speed gains, and again, it was just hard to run the algorithm past this size for the most part. Here is about a little bit more evidence on the unique contribution of switching to RCPP and big memory for us. Here we've got the new and current setup in lobster color, and in blue we've got the same algorithm, the exact same algorithm, but in base R. And you see that the speed gains are dramatic, particularly once you start getting to around n equals 5,000. And so we're very happy with that basic choice. Okay, so you know, whenever you do statistics, you run into the fundamental problem of statistical inference. You don't get to observe people under both scenarios, and so the way that this algorithm works is to sort of counterfactually imagine that each person got the treatment versus didn't get the treatment, or everybody was a man versus everybody was a woman, or whatever exactly we're counting as a binary variable. And we can rewrite that since each of our fitted estimates are going to be K, C star hat. We can just rewrite it like this in terms of what would the kernel be, and then what are the first differences there. So we're estimating this vector, this n-length vector delta, and we're just kind of, for indexing purposes, we're going to say some binary variable b. So the original algorithm, which does this, follows a little bit more the logic of linear algebra, and which makes sense, but it hits some snares. And it works sort of like this. The idea is you construct two copies of X where everyone's counterfactually assigned to 0 and 1. And then you get a new kernel, and then you retain a portion of it. But since you have 3n is the length, or is the number of rows in this, you wind up temporarily creating something that has a 9n squared memory footprint. And so this is why we noticed an outsized limitation on sample size when you started working with binary variables. So our first step was to only construct what we really care about. And what is that? It's this portion that's equivalent to, it's a partition matrix, if you want to think of it that way, where each of those partition matrices is n by n. And we're not comparing the two counterfactual scenarios directly to each other. What we're doing instead is comparing the counterfactual scenarios to the observed data. So everybody gets a 1 versus the actual data, and then everybody gets a 0 versus the actual data, and then we can kind of see what direction we seem to be pushed by that assignment. And when we switch to that, we actually hit further problems because the variance estimates, the uncertainty estimates require doing a triple product such that you wind up having to construct a, well, we'll see in a minute, but you wind up having to construct a 2n by 2n, or there are really 4 of these matrices that get constructed by way of the matrix multiplication, and it's just huge, and it's very intensive, and so we wanted to work around that variance calculation. So here's how we did that. First, we made use of the fact that we're working with squared Euclidean distance, which really plays nice. We have the sum of squared differences, and we have exponent here, and so we're able to. Oh, I might have dropped a negative sign in the slide, but the idea is we're able to put just the variable that we're looking in. We're able to bring that out front and separate it with everything else. And so we're going to call just the difference on this particular dimension, we're going to call that phi, and we're going to call the similarity score for all the other variables, we're just going to call that k star. We're going to, the reason we're calling this Boolean is we're hoping that something like a little Boolean truth table can simplify the number of scenarios and therefore make it so we don't have to do as much linear algebra in the first place. And indeed, we can do it like that. And I'm not going to walk through all of these because it's in the paper there. But here's the idea. Well, if in the data both respondent I and respondent J, well, if they were both 1s, well, when we counterfactually assign them to 1, nothing's going to change. If I and J were both 0s, when we counterfactually assign them to 0, nothing's going to change. And otherwise, we can adjust by some term phi. And then therefore, we can re-express the first differences in terms of 1 of 2 ratios and 1 of 2 sign directions. And those ratios and signs correspond perfectly with the Boolean truth table. So that's very helpful there. So this is the variance calculation that we need to do. We have the variance of the coefficients, the variance covariance matrix of the coefficient estimates. And then we have these partition matrices for the 2 n by n kernels. And then once we do that, we wind up with this, basically 4n squared size matrix, but it looks kind of like this. And we were able to factor things out a little bit, in part because we're interested in a point estimate at this point in the algorithm, and so we're able to do a little bit of factoring that we wouldn't have been able to do if we ever needed to retain these things. So that's a bit of the flavor, and so with that, we're able to reduce the memory footprint. That's Mary. She normally leaves her work a touch earlier. We're able to bring the memory footprint in line with the continuous variables, and so this is really no longer a limitation on sample size. And so here are some tests, some early tests of the Boolean estimator. And what you see here is that we wound up doing it both ways. One with pure linear algebra, that would be this one in blue, and then the other with this more customized approach where the loops really directly reflect stuff I was just discussing. We're not getting big speed gains this way. I mean, either way we've done it, we're getting better speed than the base R algorithm. But the point is that we are not losing speed, and we're gaining tremendous sample size ability by this switch. And so so we're happy with how that's going. I suspect that as this grows larger, what we've switched to will do better and better relative to the linear algebra approach. Okay, so just a few quick notes, then we'll have a bit of discussion. Is kind of this question of whether we can have all the things that we would like to have, ideally. And here's a bit how I think of it. I have on the x-axis here the number of parameters. I don't think I might have to move my screen. So we have the number of parameters here, and then we have the number of observations. And here's kind of where we'd love to be, and kind of where your typical social science methodology class teaches you ought to want to be. Is you want to have lots of data, and you want to have relatively few unknowns, and you want to be able to get nice, clean estimates of them, and you want to make nomothetic, that is law-like claims. You want to be able to say that these relatively small number of variables explains an awful lot. Increasingly, as particularly since kind of the computer revolution starting in the 1990s or whatever you would put it, but as real computing power became more available to more people, there is this possibility of saying, well, we can be quite flexible. We can consider lots of diverse scenarios, and we can be ideographic in the sense that we can really give a rich description of the data, of the causal processes, and almost, so to speak, almost have a qualitative description of everything that's happening in a particular place at a particular time. But even as we've illustrated today, even with as great as computers are, scalability is a constraint, and you can kind of imagine, so to speak, at any given feasible number of parameters and sample size, maybe you kind of learn similar amounts over here that you do over here. And so we've discussed a dramatic example of BigKRLS, which is kind of way down here. OLS, if you meet the assumptions, it's way up here. And there are also lots of kind of minor changes along this line. You could think if you're doing Bayesian Markov chain Monte Carlo, you can always allow more parameters to vary. You can always have a more complicated hyperprior structure. You can always model features of the dependent variable like zero inflation, and it's going to kind of keep pushing you to more parameters to worry about, more computational complexity. And so we've kind of seen this spectrum here, and this is a little bit how I think about data science as some combination of math and computer science and actual applied problems, and doing our best to push this frontier. What are we doing here? Okay. So we're increasingly interested in our nice, mathematical properties. For example, being able to say that the regularization parameter exists in a unimodal space, or whether it's just something more basic like unbiasedness, with some of this flexibility and robustness to not knowing exactly where the data came from, and to still have a good predictive accuracy. I think there's probably there is a crisis right now within political science on the forecasting front, where so many of us did not see this coming. So we want these kind of goals, but we also want to, insofar as possible, maintain interpretability. That is just key not only for your own understanding of what's happening, but communicating to larger audiences. And we think the BigKRLS really offers you a nice capacity to have interpretable results. However, if you try to do everything at once, you may well hit this scaling problem. We've done what we can to expand this particular technique, and we hope that some of our advances here can extend to related techniques in the near future. Things that we'd like to do with this package before too long is integrate some data reduction options. A number of people have actually mentioned to me that it would be nice to combine, at least in some fashion, maybe it's even just a vignette, but something with how does this work with something like random projections for when you know 25,000 is just not going to cut it or something. Although I will say briefly on that front that because you're getting so many estimates of the marginal effects, you're sort of happier with a small 10,000 estimates than you would be with other techniques. And we can kind of save that. And I think that this technique in particular can be particularly important since it's all grounded in similarity measurements, where for research questions where geography plays an important role. You could think police shootings, everything is kind of neighborhood to neighborhood. And so we hope to do our work with. And yeah, well, thank you very much. Thank you for your time and attention. The slides are up, and you can install this on GitHub, and look forward to your questions.
Thanks, Pete, for that presentation. At this point, Pete Mohanty is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And while we're waiting for some questions to come in, I have a couple of questions. So, you know, Pete, you brought up the election. I was hoping we wouldn't talk about that today, but you opened the door, so let's talk about it. So do you obviously it's too early to really have any kind of intelligent or certainly definitive analysis of what went wrong, but in order for your technique to improve on what was sort of going on there, it would have to be the case that the reweighting schemes that the polling-based forecasts we're using were bad, and that KRLS would improve on those weighting schemes, presumably by being more efficient given the assumptions they were making. Because my understanding is most of those reweighting schemes are essentially trying to be totally non-parametric, which means that they're totally, well, either they're linear, which is very parametric, or they're totally non-parametric, just trying to sort of do a sort of matching exercise. Do you think that that's what's going on here? And so what we really need is a better model process, post-polling model processing algorithm to get better predictions?
I certainly think it can help, and I looked into this a bit. I mean, at some point there's a question of whether you just need better data. The team at USC that worked with panel data, I think that's certainly the way to go. I did a little bit of work downloading the national polls and kind of attempting to control for differences between how the polls were done to the extent that that's publicly available and who is doing the polling. And I came up with an estimate that was more in line with Nate Silver's skeptical estimate, but it wasn't the correct. It was still off by a couple points. So you can only do so much with data that's not answering the right questions, or that's sort of not being transparent, as you say, about where it's coming from, and leaves you in the lurch. I do think that this done locally, particularly if it was combined with geolocation data, even if it's not all the way down to zip code, this would do extremely well compared to some of what we've seen out there.
Let me ask a question about interaction or conditional relationships. So a linear model or a highly parametric model that doesn't explicitly allow for conditional relationships is obviously going to, best case scenario, compute an average effect. Worst case scenario, produce just a wrong relationship. Is KRLS, because KRLS is sort of trying to be sort of closer to the data, is it going to be better at picking up those conditional relationships?
Oh, for sure, and in a few different ways, but because you're getting, for each X variable, you're getting n estimates of the marginal effect. Mm-hmm. And so if the variable you're interested in is the treatment of receiving a postcard, you get to learn that actually is conditioned by age, and it's pretty dramatic for certain age groups, and then the certain other age groups have relatively similar. So in some ways it gives you a lot to wade through, and you have to take your time to interpret that. But once you do, you can kind of say, look, I could actually probably put most of these people in the 3 or 4 groups as to whether the treatment really mattered for them.
Well, the reason I asked that was because when you did your election postmortem, you mentioned certain groups, and my understanding, just sort of watching the news, is that there were significant conditionalities. So, for example, women might well have gone for Hillary, but white women did not. And I noticed that your little I don't have your slides pulled up, but recalling the graph in your slides, you didn't have that kind of breakdown. I was wondering if you found that stuff.
Oh yeah, you can certainly look at all of that. I mean, because you can just compute the average. You can compute the average by different groups. So you could do white women. You could do by every single racial category. You could the effect of being a woman, or and so you have that, and you could look at it the other way too. The effect of every single racial belonging category broken down by gender. And you just have all that once you've got your estimates. And so.
So the ultimate non-parametric estimate is something like the Nadaraya-Watson estimator, right? Where you're just sort of taking a kernel weighted average, and then you can, and that as you know has a significant cursive dimensionality problem, right? You need a massive data set to really get good answers, and then you have something like OLS, which is highly restrictive, but also very, very fast and reliable. And when your assumptions are correct, it's going to be more efficient. So where does BigKRLS, I mean, I really should be asking this question to Jens, I guess, but where does BigKRLS stand on that continuum?
So in their original political analysis paper, they do a kind of simple simulation that shows that BigKRLS actually does better than you would think in terms of efficiency. But it is a point of comparison that we're interested in for more complicated models. I think that the virtue and the vice of BigKRLS is that it's working with n by n. But if you think of OLS, when you solve for the estimates, you're ultimately inverting a matrix that only reflects the number of parameters. Whereas here, you are working with these pairwise comparisons, so that's n times n minus 1 divided by 2. So you're actually, for any given sample size, you're just considering a lot more possibilities. And I think that it sort of makes BigKRLS appear to hold its own in terms of efficiency in ways you might not quite expect, because it's looking at approximately n squared over 2 things for each.
Well, here's where I'm going with this question. So your contribution here is making BigKRLS more feasible for data sets, but a lot of the action in data science, at least as I understand it, is in trying to make models like OLS, which are fairly simple and very, very fast on the data sets we deal with, work on massive, just staggeringly large data sets. And if we're having trouble making BigKRLS fly on a data set of 5,000 or 10,000 observations, how can it possibly work on how can it possibly hope to work on a data set that has 10 million or a billion observations? And I'm basically, what I'm asking here is should we be thinking about using models like BigKRLS on smaller data sets, or should we be thinking about putting more data into the models that are very well optimized, very fast, and we've used for years?
So I think splitting the difference. I mean, this is never going to work for high volume data. I think that I worked out once that once n crosses 200,000, this algorithm would start requiring multiple terabytes of RAM. And so that's just not going to fly. On the other hand, if you just use OLS on a 10 million person data set, everything is going to be statistically significant, and you're not really going to have any ideas of what's going on. And so what we think the direction is more like, selective inference would be one option, which is where you would have your large data set and you would run BigKRLS on whatever your computer could do, 20,000, something like this. And then you would make your choices about what your final model is going to look like, and then you'd have the rest of your data set, maybe a million. But you would actually, the idea of selective inference, which is kind of increasingly popular around here, is to then condition the p-values of of the final model on what you observed in this really intensive look, the first round of the model. And so,
you're arguing for KRLS as sort of a somewhat more informed version of exploratory data analysis on a subset of the data.
Yeah, I think in that context where you have lots of data, and then there's kind of an open question there of how best to do that. Selective inference could be one approach. Another could be something like random projections to reduce the reduce the data first and then do it that way. But we basically think that this is because it's basically so nuanced and allows you to consider so many different potential interactions that we kind of like it as a first step.
Well, it's afternoon, so that's all the time we have for this week. I want to thank Pete for appearing today, and I also want to plug next week's talk. So next week, November 18th at noon Eastern, we will host a panel discussion with a group of scholars from Women Also Know Stuff, Emily Bolio, Amber Boydston, Yana Krupnikov, Melissa Michelson, and Christina Walbrecht. The discussion is called A Discussion of the Role of Gender in Political Science with Women Also Know Stuff, Methodology, and Beyond. Please see our website, www.methods-colloquium.com, to get more information about this panel discussion and the rest of our schedule for the academic year. Pete, thanks again for appearing today.
Thank you.
Yep, and I'll see everyone hopefully next week.